Good morning to all. Electrical machine design. Design of field system. That is topic. Subject electrical machine design. Good morning to all. Electrical machine design. Design of field system. Dimensions of poles. Laminated poles with poles show forming the part of the same lamination is used for all ratings of the DC machine. First point, it improves commutation. Second, it reduces overall cost for the machine due to standardization. Design of field system. Dimensions of poles. Continuation of third point. Rectangular section referred. The square pole results in measuring of the sharp core length even though the copper requirement is less. Fourth point. The gap length at pole tips should be approximately 1.5 times the gap length under the center of the pole. Dimensions of a rectangular pole. First, length LP is equal to capital L minus bracket of 0.01 to 0.015. Axial length of pole. Second, BP. Flux density in pole. 1.5 to 1.7 Tesla or 1.4 to 1.5 Tesla. CL is equal to leakage coefficient or factor. It is the ratio of total flux in the pole body to total useful flux entering the armature through air gap. First point, CL is equal to 1.5 to 1.2. Second point, pi p is equal to CL into pi. Flux in the pole body, that is pi p. Area of cross section, net area. Third, AP is equal to area of cross section. AP is equal to pi p divided by BP. Fourth point, cross-sectional area of the pole is equal to AP divided by Ka. Ka is equal to iron factor. Gross cross-sectional area of pole is equal to AP divided by Ka. Ka is equal to iron factor. Width of the pole is equal to gross cross-sectional area of the pole divided by axial length of pole. PP is equal to AP divided by Ka divided by LP. Height of the pole is decided by MMF to be provided on the pole at full load. Field MMF required at full load and height of the pole core interrelated. Therefore, we assume the value of field MMF at full load. A large field MMF is chosen to prevent the effect of armature reaction. Full load field ampere turns per pole ATF divided by full load armature ampere turns per pole ATA is equal to ATF divided by ATA is equal to 1.1 to 1.3. That is non-interpole machine. ATF divided by ATA is equal to 0.7 to 1 interpole machine. Therefore, ATF is equal to 1.1 to 1.3 ATA non-interpolar machine. ATF is equal to 0.7 to 1 ATA interpolar machine, where ATA is equal to IA dash Z divided by 2P, where IA dash is equal to IA divided by capital K. Also, ATF is equal to HF is equal to height of field coil into ampere turns per meter, height of field coil ATF dash. Capital ATF is equal to HF into ATF dash. HF is equal to ATF divided by AT dash F. Important points. Find out field ampere turns per meter, height ATF dash. Let HF is equal to height of winding in meter. DF is equal to depth of winding in meter. Del F is equal to current density in field winding in ampere square millimeter. That is delta F. Capital AF is equal to area of cross section of conductor in field winding in square millimeter. Capital TF is equal to total number of turns in each field coil. Capital SF is equal to copper space factor. That is ratio of copper area in the field coil to the area of cross section of the field coil. SF is equal to AF TF divided by HF DF. IF is equal to current in the field winding in amperes. Capital IF is equal to del F into AF, that is delta F into AF. RF, capital RF is equal to resistance of each field coil in ohm. RF is equal to rho LMTF TF divided by AF. Rho is 2 into 10 power minus 8. That is PF is equal to permissible loss per square meter of cooling surface. Capital ATF dash is equal to ATF divided by HF. ATF dash is equal to IF TF divided by HF. That is ATF dash is equal to delta F AF TF divided by HF. Copper area in each field coil is equal to AF TF. Copper area in each field coil is equal to SF HF DF. Copper losses in each field coil. IF squared RF is equal to delta F AF bracket square into rho LMT F TF divided by AF. IF squared RF is equal to delta F squared rho LMT F AF TF. IF squared RF is equal to delta F squared rho LMT F SF HF DF. Cooling surface of field coil is equal to neglecting top and bottom surfaces. Cooling surface of the field coil is equal to 2 LMTF HF. Permissible copper losses in each field coil is equal to permissible loss into square meter. PF into 2 LMTF HF. That is del F squared rho LMTF SF HF DF. For temperature rise of field coil to be within specified limit, copper losses in field coil should be equal to permissible loss. Delta F is equal to root of 2 PF divided by rho SF DF is equal to delta F. ATF dash is equal to delta F AF TF divided by HF. ATF dash is equal to root of 2 PF divided by rho SF DF and AF TF divided by HF. ATF dash is equal to root of 2 PF divided by rho SF DF into SF HF DF divided by HF. HF and HF is cancelled. Numerator and denominator. HF is equal to ATF divided by ATF dash. HF is equal to ATF into 10 power minus 4 divided by root of PF SF DF. Capital PF is equal to 700 to 750 watts per meter square. SF is equal to 0.4 to 0.45. DF is equal to 0.03 to 0.05 meter. Therefore, total height of pole HP is equal to height of field coil plus height of pole shoe plus height taken by insulation and height wasted due to curvature of yoke. HP, total height of pole is equal to height of field coil plus height of pole shoe plus height taken by insulation and height wasted due to curvature of yoke. That is HP is equal to HF plus HS plus insulation and curvature of yoke. That is HP is height of pole, curvature of insulation and curvature of yoke is 0.1 to 0.15. Toe P, that is toe P is pole pitch. HS is equal to 0.04 to 0.06 meter. Dimension of yoke is equal to first point, flux in yoke. Pi Y is equal to pi P divided by 2. Second point, cross-sectional area of yoke, AY, capital AY is equal to pi Y divided by BY. BY is equal to 1 to 1.3 Tesla. Third point, AY, axial length of yoke into depth of yoke, where axial length of yoke 1.5 times the gross length of armature. DY is equal to AY divided by 1.5 capital L.